video will accompany the Chapter 10 notes, Statistical Inference, comparing two groups. This is part 1 of the videos. Why do we use sample data to learn about population data? Recall from previous chapters that researchers are often interested in learning about a population. Unfortunately, collecting data from every element in the population can be difficult. Instead, researchers will take a subgroup from the population known as the sample to examine. Recall that we have these 4 very important definitions. Please take a moment to review these definitions. In this chapter, we are going to continue to develop a set of tools that will allow us to take the information contained in the sample to make inference about the parameter. Recall that we will be working with the following parameter statistic sets. Previously, we primarily focused on the mean and the proportion. Now, we're going to look at a difference in means as well as a difference in proportions. Notice previously we focused on using the statistic x bar to estimate the parameter mu when working with a single mean. Now that we're working with the difference in means, we will look at the sample mean from one sample minus the sample mean of another sample to estimate the difference in population means, and similar for proportions. Previously, we looked at how to estimate the value of a single parameter using the information from the sample by way of a statistic using confidence intervals and significance test. In this chapter, we're going to look at how to make a comparison between two parameters. Section 10.1, Categorical Response, Comparing Two Proportions. For a categorical response variable, inference will compare the groups in terms of their population proportions in some particular category. In order to use the methods in this section, we need the groups to be independent. We can do all things we did with a single proportion. In other words, we can describe the sampling distribution, construct and interpret a confidence interval, and conduct a significance test. All of these will utilize the central limit theorem. Below is the central limit theorem for a difference in proportions. When choosing random samples of size n1 and n2 from the populations with proportions p1 and p2, additionally, we need both of those to be independent. The distribution of the difference of proportions has the following characteristic if the samples are random and independent. Center, the mean is equal to the difference in population proportions p1 minus p2. Spread, the standard error can be calculated using this formula. Notice this formula looks very similar to the formula when we had a single proportion, but now that we have 2, we need information from each of them. Shape, if the populations are normal, or if the sample size is sufficiently large, the distribution is reasonably normal. The larger the sample size, the more the sampling distribution tends to a normal distribution. A normal distribution is a good approximation as long as these 4 conditions are met. This is the same as having an expected count of at least 10 in each category. Previously, for a single proportion, we needed counts of 15. Here, the methods work reasonably well with slightly smaller sample sizes. For the scenario below, determine if the sample size is large enough for the central limit theorem to apply. If the sample size is large enough, compute the center of the sampling distribution and fill out the formula for the standard error. First, we will check our sample sizes. The problem states, according to the 2006 Australian Census, PW equals 25% of Australian women over the age of 25 who have a college degree, and PM equals 21.4% of Australian men over the age of 25 have a college degree. Assume that we would take random samples of 100 males and 100 females. Checking our sample sizes for women, we would need at least 10 women who have the college degree and do not out of the sample. So here we have our sample size for women times the percentage of them that have the college degree. This tells us that 25.5 women in the sample had the degree and 74.5 did not. Both of these counts are greater than 10. Doing something very similar for the men, and then combining the information together, we see that all the expected counts are greater than 10 and the requirements are satisfied. Since the requirements are satisfied, we can go through and compute the center and the standard error. Computing the center, we're going to look at the difference in proportions from the two samples. So we have 0.255 minus 0.214 equals 0.41. And then filling in the formula for standard error, we have the following. Next, we're going to look at confidence intervals for a difference in proportion. Recall that our goal is to learn how to translate the information contained in a single sample to learn about the parameter. The most simplistic way to do this is to use a point estimate. Recall that a point estimate is a single value estimate of the parameter we are interested in learning about. It is our best guess. The statistic from the sample can be used as a point estimate. We know due to sampling error that the statistic or the point estimate is rarely exactly equal to the parameter. Instead of using the point estimate, which is a single number, we can use an interval estimate. An interval estimate gives an interval of plausible values for the population parameter. One common form of an interval estimate is known as a confidence interval. Previously, we saw the generic form of a confidence interval is the statistic plus or minus the margin of error, where the margin of error reflects the precision of the sample statistic as a point estimate for the parameter. The margin of error is constructed by taking into account the standard error and the percentage of intervals that would cover the parameter based on the behavior of the sampling distribution. Consider the following example. Ecologist will sometimes use tags placed on birds to track and learn about the birds. The tags are typically small metal bands that go around the bird's leg. Recently, ecologists have started to use electronic tags and are interested in learning if there's a difference in the survival rate between the two types of tags. A study looked at 10-year survival rate of swallows tagged either with a metal tag or an electronic tag. 20% of the 165 metal tag swallows survived, compared to the 36% of the 200 electronically tagged swallows. The margin of error for a 90% confidence interval was found to be 5%. We are interested in a 90% confidence interval for the difference in proportions. We will list the metal tag first and assume we have independent random samples. Looking at the fully worked solution for this problem, we first notice that we are working with different proportions. In order to satisfy the sample size requirement for the central limit theorem, we would need to check the following. This is the same as having a count of at least 10 in each category in each group. So of the metal tag group, notice we have 33 survived and 132 died. In the electronically tagged group, we had 72 survive and 128 die. All counts are greater than 10. Additionally, we have independent random samples, so the requirements are satisfied. From here, we can calculate our statistic, which is going to be the difference in the percentage of the two types of tags that survived past the 10-year rate. So we have 20% minus 36%, or 0.2 minus 0.36, giving us a point estimate of negative 0.16. Also, we're given that our margin of error is 0.05 for this example. So to calculate our 95% confidence interval, we have the following. We're going to take our statistic plus or minus our margin of error, which gives negative 0.16 plus or minus 0.05, resulting in the interval negative 0.21 to negative 0.11. Our interpretation of our confidence interval here will be that we are 90% confident that the survival rate is between 0.11 and 0.21 lower for metal tag swallows than for electronically tagged swallows. Notice here, by the use of the word decrease, or lower rather, we're accounting for that negative sign that we saw in the interval. Let's take a closer look and break down this interpretation into the different pieces that we know all interpretations of confidence intervals must have. We must always have our level of confidence. This interpretation has that we are 90% confident. We must always reference our parameter of interest. So here our parameter of interest is the difference in the survival rate for the metal tag swallows compared to the electronically tagged swallows. And then finally, we need to include the confidence interval. When comparing two proportions or two means, we're often interested in does the interval contain 0 or not. If the confidence interval contains 0, it's plausible that our proportion from our first population is equal to the proportion from the second. If the interval is entirely below 0, this would indicate that the first group is the first proportion from the first population is smaller than the proportion from the second population. And if the interval lies entirely above 0, this would indicate that the proportion from the first population is larger than the proportion from the second population. In summary, we have the following from your book. We'll check to see whether 0 falls in the confidence interval. If so, it's plausible, but not necessary, that the population proportions are equal. We'll then look to see if the entire interval is positive or negative. And then the magnitude of values in the confidence interval tells you how large any true difference is. If the values in the confidence interval are near 0, the true difference may be relatively small in practical terms. Recall that previously, when we first introduced confidence intervals, we went through the basic steps of calculating a confidence interval. You want to start by determining whether you're working with a mean, proportion, and now a difference in proportion or a difference in means, then identify each of the parts needed to compute the confidence interval. From here, you'll still compute your statistic and your margin of error, and then finally interpret that confidence interval. Take a moment and read pages 5 through 7 on your own. On the bottom half of page 5 is how to calculate a confidence interval for a difference between proportions. You should notice that these steps are very similar to when we computed a confidence interval for a single proportion. Just our formulas and our sample size checks are slightly different now to account for the fact we have two population proportions we're interested in. Then on pages 6 and page 7 are two fully worked examples. Again, you should notice that these examples are very similar to when we worked with single proportions, which is slight changes to account that we now have a difference in proportions. After going through the examples in those two pages, come back to the video and we'll see how to compute these problems using different technology to aid us. On page 7 of the notes, you just read how to compute this problem by hand. This problem looks at a study which was done to see if daily aspirin intake to 5 years or longer reduces the risk of colorectal cancer. Now, instead of computing this problem by hand, we're going to look at how we could solve it by using a statistical software known as Minitab. Located in your notes is the output from Minitab. This computer output will do the calculations for us. Let's look at the different pieces. First, notice under descriptive statistics, we have the information from the samples. We have each of the samples summarized, including each of the sample sizes, the number of events, so this in this case will be the number of people who died from cancer, and then we have each of our sample proportions. Underneath, we have the different confidence intervals. For your exam, you'll want to be able to read output like this to get the confidence interval. You will not be required on the exam to compute a confidence interval for a difference in proportions. You will be required to be able to compute confidence intervals for single proportions and single means, but not for the difference in proportions. So if you were going to solve this problem by hand, looking again at page 7 of your notes, you would still want to be able to check the assumptions and give the interpretation. You would not be required to do the middle portions of the problem, which are to calculate. You would just need to be able to read the confidence interval from this output. Next, we will summarize how to conduct a significance test for comparing two population proportions. This summary comes from your book. Notice that the steps here are very similar to the steps that we used when conducting a significance test for a single proportion. We're still going to check our assumptions, write out our hypotheses, calculate our test statistic, compute our p-value, and draw our conclusions. The only difference here is you won't be required to compute the test statistic or the p-value by hand. Again, we're going to use technology to aid us in doing this. In practice, for the sample size guidelines for a significance test, Significance tests comparing proportions use the sample size guidelines from confidence intervals. Each sample should have about 10 successes and 10 failures. The two-sided test is robust against violations of this condition. In the case, you can use the test with smaller sample sizes. In practice, two-sided tests work well if there are at least 5 successes and 5 failures in each of the samples. Pages 10 through 12 of your notes highlight how to use an online applet to solve a problem. Notice on the top of page 10, we have a link to the applet as well as directions on how to fill in the different pieces. On the bottom of page 10, we have an example that reads as the following. Time magazine reported the result of a telephone poll of 800 American adults. The question posed of the Americans who were surveyed was, should the federal tax on cigarettes be raised to pay for health care reform? The results of the survey were as following, and you have a table on the bottom of page 10. We're going to look at how to use an online applet to solve this problem. The solution for the problem starts on page 11 of your notes. As we talk through these pages, I'm going to bring up the online applet and show you how to fill in the different pieces. So notice on the top of page 11, the first thing we're going to do is our usual assumption check. Of the non-smokers, there were 351 that said yes and 254 that said no. Of the smokers, 41 said yes and 151 said no. All the counts are greater than 5. This is a two-tailed test, so the requirements are satisfied. Since this was a voluntary poll, the samples are likely not random, so we are going to proceed with caution here. Next, we're going to set up our hypotheses. The appropriate hypotheses for the test are, under the null, the proportion of smokers is equal to the proportion of non-smokers, and under the alternative, the proportion of smokers is not equal to the proportion of non-smokers. So here when we talk about the proportion, we're talking about the proportion of people that would say yes. So the assumptions check and setting up the hypotheses, these are something that you want to be able to do from the problem statement. If you'll recall, when we worked with a single proportion, we would always set up our assumptions, we would set up our hypotheses, and then we would calculate our test statistic. Here, you don't have to calculate the test statistic by hand. We're going to use an online applet to help us do that using your homework, or on an exam, be able to read that output from Minitab. The link for this applet is located on the top of page 10 of your notes, and you'll see here in the video is what the applet looks like. So we're going to go through and fill in the different pieces. A screenshot of this is also available on page 11 of your notes. So first, under the null, we're going to select an equal sign. Under the alternative, since we have a two-tailed test, we're going to place not equal to. Next, we need to put in the information from each of our samples. For our first group, we have a sample size of 605, and again, this information is coming from the bottom of page 10 of your notes. Of our favorable cases, we're going to put in 351. For sample size 2, we had 195 people, and of those that said yes, we have 41. Here, we're using a significance level of 0.05. Now, this is a free applet, so notice that it does have ads in it. But what you're looking for is the yellow Solve button. So click on the yellow Solve button, and it may take the applet just a moment to come up with a solution. Scrolling down to the bottom, you'll now see that we have the solution. The solution is also copied for you on page 12 of your notes. Looking through here, the solution will first summarize the two samples for you, as well as summarize the pieces that you need to compute this hypothesis test. You'll notice that these formulas that they're using match up with the formulas that are given to you on page 9 of your notes. They also go through and set up the null and the alternative hypothesis. This applet also gives what's known as the rejection region. We're not using the rejection region in this course, and you'll notice on page 12 of your notes, this has been grayed out. Here they compute the test statistic for us. The decision about the null hypothesis, the first part is based on the rejection region, and again we don't use that, so you'll notice it's grayed out in your notes. And then we have our conclusion. So you can use this online applet to get your test statistic as well as your p-value. And then you'll always want to make sure you give your conclusion in context of the problem, which is given on the bottom of page 12 of your notes. So notice that the applet computes the test statistic and the p-value for you. You still have to be able to check the assumptions, set up the hypotheses, and give the interpretation at the end of the problem on your own. Next, we're going to look at how to solve this same problem, but here we're going to use output from Minitab. So we're now on page 13 of your notes. On the top of page 13, notice that we have that same problem again. But now we have some output from Minitab. Looking at the output of Minitab, we now have the descriptive statistics, which remember give us our summary of our sample. And then at the bottom, we have the information from the significance test. Notice that the z-value and the p-value are the exact same test statistic and p-value that we have on the previous page, page 12 of your notes, that the online applet gave us. So again, for an exam, you will not need to compute the test statistic and p-value for a significance test for a difference in proportions by hand, but you will need to be able to read the output, such as it's located here. So let's work through a full example where we're given the Minitab output and see the different pieces that you would need to include. Here our example reads, the Women's Health Initiative conducted a randomized experiment to see whether hormone therapy was helpful for postmenopausal women. The women were randomly assigned to receive the estrogen plus progestin therapy or a placebo. After 5 years, 107 of the 8,506 women on hormone therapy developed cancer, and 88 of the 8,102 women on placebo group developed cancer. Is there a significant difference? You may assume independent random samples since this was a randomized experiment, and we're going to test at the 0.05 level. So the very first thing that you would need to do in a problem like this is to check your assumptions. So notice of the therapy group, 107 developed cancer and 8,506 did not. Of the placebo group, 88 developed cancer and 8,102 did not. All counts are greater than 5, so the requirements are satisfied. Additionally, we are given that there were independent random samples. So first we've checked our assumptions. Now we can set up our hypotheses. Here we're trying to prove if the proportion of women who develop cancer under the two different treatments is different. So under the alternative, we have P therapy is not equal to P placebo. Under the null, we will set up the two as equal. Next, we're going to use the output on page 14 to identify the test statistic and the p-value. Notice here we're given that our test statistic is equal to 1.03 and our p-value is 0.304. Since our p-value is greater than alpha, we are going to fail to reject the null. And then as our last step, we can give our interpretation. So at the 5% significance level, we do not have enough evidence to conclude that the proportion of patients on therapy who develop cancer differ from the proportion on placebo that develop cancer. This concludes the first part of the Chapter 10 video.